So good morning to everybody, and now we are going to go with the fifth and second last recording of our today's lecture, and what I'm going to talk about are subsequences. Subsequences are perhaps the most difficult, the most interesting and the deepest topics of all the course. It seems strange. I don't think that functions, derivatives, and integrals are really elementary things and so on. They are extremely important and so on. But from the conceptual point of view, the role of the subsequences is extremely important. So, what does it mean, subsequence? It means take a sequence, use just a subset of the element of the sequence, keeping the same order as in the original sequence, and construct with this infinitely many elements extracted from the original sequence, construct a new sequence. Okay? So let us start with an example, and so consider an as minus 1 to the nth power n. Remember that notwithstanding what some books say, this is not a divergent sequence, okay? But consider just the even elements a to n, so the index here is even, which means that you take minus 1 to the power 2n, n, minus 2n, minus power to the minus 1 to the power 2n is equal to plus 1, because the exponent is even, so this is equal to 2n, and this is positively divergent. This goes to plus infinity. The original sequence was not positively divergent. This sequence made just of elements, of some elements, in particular the even elements, is positively divergent. Vice versa, consider a to n plus 1. So the odd elements, this is minus 1 to the power 2n plus 1, that multiplies 2n plus 1, and this is of course equal to minus 2n minus 1, and this goes to minus infinity. Okay, so there is another sequence made of the elements of the original sequence and kept in the same order that goes to minus infinity. And now the idea, what is a subsequence? So definition here. No, it's really not a definition. I want to give you the idea. Definition complicated, I will give you later. So intuitively, a subsequence of a given sequence is a sequence. So a subsequence is a sequence in turn, so an infinite ordered list of number of a given sequence is a sequence made of course they have to be infinitely many, element of the original sequence what is extremely important, they have to be taken in the same order. So pictorially, consider a situation like the following. You have the elements of the original sequence that are A0, A1, A2, A3, A4, A5, A6, and so on and so on. And you choose some of them. For instance, this A0, that will be our B0 element of of the sequence, then A3, this will be B1, and then of course A4, this will be B2, and so on and so on. So this red sequence made of Bj, of elements Bj or Bk, will be the new sequence, the subsequence. So the sequence B, let me call it Bk. I could also call it Bn. It is not another the name that we give to the labels. This is a subsequence of the original sequence. Okay, and notice that we kept the same order. So B naught is A naught, and it comes before B1, which is A3. So in extracting elements for the original sequence, there is no exchange of order. Okay, sequence Bk is a subsequence of An. A comment that will be quite useful later is the following. Notice that Bk is equal to An for every k. Okay, for every k there is an n such that. So k is always less or equal n. This is why we extract just some elements, not all of them. In any case, the index of the B cannot overcome the index of the corresponding A. Here the index is 1, and the corresponding A has an index 3, here 2 and 4. Okay? K is less or equal than n. Moreover, since for every k there exists n, and it is unique, there exists a unique n such that Bk is equal to An, one can introduce nk as the correspondence between the two indices. In the figure we have n naught. So when k is equal to 0, n is equal to 0, so n naught is equal to 0, n1 is equal to 3, n2 is equal to 4, is equal to 4, and so on and so on. Moreover, nk, which is a sequence, is a monotonic, strictly increasing sequence of so with natural values. Okay, I just wanted you to observe this feature of nk in order to use it for the definition, for the official rigorous definition of subsequence. Okay, so definition. You should be not surprised now because I showed you all the elements of the definition, but let us go. Let an be a sequence and nk be a strictly increasing sequence of natural numbers. Then the sequence bk is equal to a and k, like in the previous example, is called a subsequence of an. Okay, this is the official definition, and so I think I don't wanna give other example because it is quite clear. I just repeat the remark I already gave you that says that since nk is a strictly increasing sequence of natural number, of course we have nk larger than or equal to k. Okay, and now let us go to the first theorem, which is very simple and says the following. Oh, sorry, I have a problem. Okay. Here. So the theorem says let an many problems here, sorry. What happens here? Let an be a sequence okay. Okay. Let an be a sequence that has a limit. And this limit can be finite or infinite. Namely, the sequence may be either divergent or convergent. It's regular, okay? Then every subsequence of an has the same limit. This is intuitively true because if a sequence, for instance, consider a sequence that is going to plus infinity, you extract elements without changing the order. Of course, with the new elements, you form a new sequence that goes to plus infinity too. Perhaps it goes faster than the original one. However, this is the theorem, and I give you the proof. So the sequence is an, let bk is equal to a and k, a subsequence of an. First case, the first case is an is convergent to some limit L, which is a real number. We want to show that the subsequence converges to the same limit. So, as usual, when you want to show that something converges, you say let epsilon larger than 0, arbitrary. And then remember what is the definition of limit. Since an goes to L, then there exists n bar such that whenever n is larger than n bar, then the distance between the sequence n and the limit L is less than epsilon. Okay, now you say consider k, the index of the subsequence, larger than n bar. Then, for the previous remark, nk is not smaller than k, which is larger than n bar. Therefore, the distance between bk and L equals the definition of a subsequence, the distance between a and k and L, and this will be less than epsilon. Then by definition of limit, since we found n bar such that after n bar the distance is less than epsilon, so we have that by definition of limit we have that bk converges to L. Of course, there are other two cases. The second case is an is positively divergent. Third case, an is negatively divergent. I leave these cases to you as a homework. They are very simple. So this is the first result that tells us what happens when the sequence is regular. Okay, when the sequence is regular, then you are done. In the sense that every subsequence goes to the same limit. And what happens when the sequence is not regular? And here I give you the theorem. This is the most beautiful theorem of all the course, with really a striking proof, and I discovered this proof on Wikipedia. Okay, I don't want to tell you anything about that. See Wikipedia. The word that you have to search is Bolzano-Weierstrass theorem. We will see also the Bolzano-Weierstrass theorem. It is not so beautiful. What is beautiful is this lemma. Now, you don't know any other construction of the analysis, but if you go to books, you will see that this lemma or theorem of Wiki Theorem, let us call us Wiki Theorem, it has not a name, is really a strong shortcut in our theory, and it is very simple to state and wonderful to prove. And it says the following: every sequence, without hypothesis, every sequence has a monotonic subsequence. It's almost poetry, okay? There are no formula, it is very simple. Every sequence with no further hypothesis has a monotonic subsequence, and monotonic, we cannot specify whether it will be increasing or decreasing, but you will always be able to find a monotonic subsequence. Let me give you the proof of this wonderful theorem. This is wonderful. And the proof says, okay, first, a picture. Okay? This is, because if you understand the picture, then the proof is really just a description of what happens on the picture. Consider a sequence portrayed as a graph. So here you have n, here you have an, and for instance, here you have a0, here you have a1, a2, a3, a4, a5, a6 here, a7 here, a8, a9, and so on and so on. Okay, this is for instance the picture of the graph. The graph here is not extremely expressive, so just join by segment every element. So a0 with a1, a1 with a2, a2 with a3, a3 with a4, then a5, then a6, go to a7, a8, a9. So here I want you just to see what is the first idea. The first idea can be the following. So consider this, the tallest points, peaks. You see, here there are these peaks that form a monotonically decreasing sequence. Okay, so this is a peak, peak, peak. So the first idea is that peaks form a monotonic decreasing sequence, provided that they are infinitely many, because we are not guaranteed that they are infinitely many in order to form a sequence. We need also to specify what is a peak. I relied only to your intuition and on your knowledge of mountains. My knowledge of mountains is really bad. I come from the seaside, so sorry for that if I say something stupid about mountains. But I like them, but I'm very ignorant on them. But mathematically, the idea we need a peak is the following. If you are on a peak and you look towards infinity, you don't see other peaks. So this is a peak. This is a peak. Okay, all the others are blocked if you go from here to the peak here. So it is not just being a local maximum, okay? you look at the horizon at infinity and you see the horizon without being blocked, without your sight being blocked by some other peak. This is important, okay? And because otherwise it means that there will be another peak taller, and then you will no longer have a monotonically decreasing sequence. So this is the first point, the definition of a peak. And let me write it. So preliminarily, we define a peak to be every element of the sequence AN such that AN is strictly larger than AM for every M larger than N. This means exactly what I said. You look towards the infinity and you don't see any other peaks because all subsequent elements are smaller than the peak you are on. Okay, now, very simply, if AN as a sequence has infinitely many peaks, then the sequence made of all the peaks is monotonically strictly decreasing. And then there is the other. And then there is the other idea. The second idea is the following. So let us do another picture here. Let us draw another picture, and so the picture is here. This time you have finitely many peaks. And so on and so on. Okay, stop here. Here what happens is the following. You have only one peak. For instance, this guy here. This is the only peak. Now what you do if you have only one peak? You go after the last peak. So you start from the second element and you say, this is B naught. Now, there are no longer peaks here in this part of the sequence. So, after B naught, there will be an element which is taller than him, which is larger. And for instance, this guy here, B1. B1 is not a peak. So, you will find an element that is taller than him. You look at the horizon and then you are blocked. And so you select the second. This is B2. B2 cannot be a peak because the only peak was B1. So by definition of peak, again, there will be another element that is blocking its side toward the horizon. So, and this is B3. And so on and so on. Okay? And in this way, you have infinitely many elements and that form a monotonically increasing sequence. Okay? Just describe this process and then we are done. If AN has finitely many peaks. So if an has a finite number of peaks, let n tilde be the index of the last peak an tilde, sorry. So now define B naught, the first extracted element, the first element of the subsequence, equal to a n tilde plus 1. Of course, it is not a peak. It is not a peak of an because an bar was the last one. The last one exists because the peaks here are finitely many. Then there is an element n tilde, an element am tilde with m tilde larger than n tilde plus 1, so larger than the last element, such that am tilde is not smaller. Again, problems with pen, sorry. Let's wait just 1 minute. However, am tilde not smaller than B naught. So define B1 equal to am tilde, then B1 is larger or equal B naught. And again, we go iteratively, again, since am tilde is not a peak, then it is possible to find and choose another subsequent element in an such that B2 is larger or equal B1 in such a way that the resulting sequence Bn is monotonically increasing. Okay, stop here, and in the last video we will see the Bolzano-Weierstrass theorem, and then we will start to talk about limits of function.